Yeah, so my name is Tiago. I'm a OpenEBS maintainer and occasional maintainer of Paperclip, if you know that. Probably you don't. And I've been working for DataCore for probably a decade now. And for the past 5 years, I've been working on the OpenEBS project and its various engines. So I'm going to cover several tips and tricks and traps that myself and some of our users have faced when using storage solutions in Kubernetes, and hopefully that's going to be helpful. Right, there's this. So first, perhaps just a few words about some of the ABCs of Kubernetes. So Kubernetes has emerged as the de facto container orchestrator, among others, for example, Docker Swarm, etc. Kubernetes started mostly focused for stateless applications. However, stateless applications. However, stateful applications are really critical for many business use cases. So Kubernetes has been making strides for better supporting stateful applications. So just a few bullet points on why stateful services can be preferred for maintainability. So they can be more lightweight because there's less CPU and memory usage trying to write to storage, for example, not in all cases. Less complex, there is no state maintained across requests. Data is generally maintained out of the service, and it is easier to scale. By this fact, it's also more fault tolerant. The service is decoupled from the data. Restarting the services comes with no significant data loss. And as we will see, restarting with data can be quite tricky. Conversely, stateful services come up with more challenges. Persistent storage needs to be carefully managed. Scaling is more complex. Data needs to be correctly replicated and synchronized across n instances. Some examples are databases, message queues, financial services, etc. So let's talk about volumes now. So in Kubernetes, you really have three basic kinds of volumes, which are the ephemerals. They share the lifetime of a pod. So mtdir or config map. And by this, it means when the pod is down and recreated, all that data is gone because it's ephemeral. Persistence, well, these ones are the ones we like. They persist beyond the lifetime of a pod, and you can achieve this using CSI and even some of the old in-tree drivers. Then a very special kind of projected volumes, which combines informations from different resources into a volume. So we're going to focus on persistent volumes. So how do we actually use this so-called persistent storage? So let's have a look at some of the existing APIs. So a PVC, is persistent volume claim, is a request for storage to use in the pod. And pod is the smallest unit of execution in Kubernetes, and it contains one or more containers. So this request specifies generic storage parameters, such as the volume mode or capacity, for example, 10 gigs, 20 gigs, and the storage class name, which hides somewhat opaque parameters, as we'll see. Yeah, just a simple example of a storage class. Storage class name, and it's a file system. The somewhat opaque storage parameters I mentioned are specific to provisioners. It might be fin provisioning, access protocol, which is how is the volume actually attached to the host where the application is running. And VMF is one that's been using more lately. There's also iSCSI, vhost, and even loop devices. Some drivers also let you choose which file system you want to use, XFS, BTRFS, ext4, etc. Then there's a less opaque one, such as mount options for your file system and the volume binding mode. And I'm going to touch upon the volume binding mode a bit later. So here we can see some common parameters in blue, or the last three, which are the reclaim policy, the binding mode, and whether this volume can be resized to a larger size. And then in green, you can see the parameters which are very specific. In this case, it's the OpenEBS Mayastor CSI driver, and the protocol is NVMF. You can specify 3 replicas, and it will create fin provisioned volumes. Persistent volume, or PV, this is what actually represents the actual storage from your storage backend. And it can be manually created, static provisioning, although this tends not to be used anymore. The new way of doing it is dynamic provisioning, which means the PV is created in response to a PVC creation. So it satisfies all the parameters that you specified on the storage class. Just some example of a PV, and you can see some on the volume attributes, protocol and number of replicas, just like the ones I shown before. So how does it all fit together? We can break down the life cycle of these volumes in 5 stages. First one is provisioning, which, as I said, could be static, where admins set up the PVs, and dynamic, where the PVC is actually created by a user, and the PVs are then dynamically created based on the storage class you specify. Binding is actually the act that binds the PVC to the PV. Then using the volume, this is when the pod actually consumes the volume. And in some cases, for example, the volume isn't really completely configured until you use it. For example, maybe the file system is only created on the volume when you actually use it. That's, for example, how it happens on our CSI drivers. Then reclamation is when the volume is not being used. Then we can release the binding, and we can reclaim the storage back. And there's different options, retain and delete. We're going to cover them as well. So there's different access modes. What does the access mode actually mean? For example, read-write once means that the volume is mountable as read-write by a single node. Read-only many is read-only by many nodes. Read-write many is read-write by many nodes. And read-write once pod, read-write by one pod. And this is actually interesting that a lot of users get confused with this, me initially including. And we're going to see later what the issue is. So just to recap on what I mentioned before about the pod, it's the smallest unit of execution, composed by one or more containers. It can consume no volume, or it can consume one or more volumes. And it's a basic building block for deploying a service in Kubernetes. So typically, probably users shouldn't use the pod directly. Stateful sets and deployments actually make use of the pods, and they are an order of magnitude abstraction above the pods. So they leverage and they manage and they update pods so that you don't have to. Take some pain away from it. So, that's interesting. Okay. So what's the difference between a stateful set and a deployment? I guess you could say that deployments are more like cattle and stateful set like pets. So each stateful set pod is handled with a little bit of extra care. It's expected to have its own state, its own persistent volume, and a network name which is unique and it's persistent. Rolling back a stateful set can be kind of complicated. How do you roll back? You can roll back all the metadata related to the pod, but how do you roll back the actual data? So you could use snapshots to keep track of the persistent data, although there is no way today of reverting back, at least that I know of, a PV to a snapshot in a standard way. It will have to be some CSI specific to the CSI provider that you're using. So I'm going to cover some tips, tricks, and pitfalls when dealing with storage. So one that people make a lot, so stateful sets versus deployments. Actually, a deployment can still mount a volume, or rather pods in a deployment can still mount a volume. The difference is that deployments don't support claim templates. That means the volume has to be shared by all of the pods in the deployment, which typically brings the read-write-many volume mode as a requirement. Excuse me. And not a lot of CSI drivers support read-write-many volumes. And another important thing here that I'm, sorry. Stateful applications, typically, they don't store data in the cluster, or they don't rely on persistent data across restarts. And this is important, because it means that a stateful application can still use a volume, but it's just not requiring the data to be present when it restarts, for example. So you should prefer deployments for stateless applications, even if you use volumes, provided that you don't require them to be persistent. In some cases, you can also use pods yourself. So for example, Cloud Native PG operator actually doesn't deploy stateful sets, that it actually deploys the pods directly. But then you have to manage them yourself. In this case, the operator does it. So let's do a recap of the reclaim policies. So the retain option allows for manual reclamation of a storage resource. When the PVC is deleted, the PVC is simply released from the binding. And it can now be used by another PVC, for example, or it can be deleted if no longer required. So all good so far, but there is a lurking danger. When you delete the PV, there's no cleanup associated of the associated storage asset. So that means you would actually be leaking the data because no one thought to tell the storage provider, hey, this PV is now deleted. So you have to know how to manually clean up storage from your storage provisioner. So this can lead to storage leak for the unassuming user. And we've had some reports from our users on OpenEBS MyStore, and we actually have an option now to garbage collect these orphan volumes so that the user doesn't have to. So this is another interesting one. Not sure if it's a bug or it's just a side effect of the previous thing, but attempting to delete the PV ahead of the PVC again may lead to leakage of the storage volume. And maybe not everyone has this workflow, but we've had some users do this as well, where they start to delete the PV. It won't delete because the PVC is still using it, so they cancel the request, and then they delete the PVC, and then the data is leaked. And here I can see it's leaked because even though the PVC and PV are gone, I'm using the kubectl MyStore plugin, and the volume is still available in MyStore. So we've also added a feature which will clean up these volumes automatically. So you should check with your CSI provisioner what happens. So while preparing for this presentation, I actually found out that Kubernetes now has a workaround for this, using the, I think, under PV reclamation policy. And it requires, or it's stable on Kubernetes 131, but it requires a recent version of the CSI external provisioner. So depending on whether your provider has the latest version, they might work or not. So consider what happens if a volume is created on a certain node in a certain zone, but then your application is started on a different zone or a different node. So this means you'll have a network penalty for the storage I/O, even though you might actually have storage on the node where the application is running. So using the wait for first consumer is quite useful in this case. It allows for storage placement optimization. And how does it work? When you create the PVC, the PV is actually not created until it's first being used by the pod. And this allows orchestration to guarantee that the volume is created on the same node where your application starts running. So remember the access modes we covered previously? So read-write once is mountable as read-write by a single node. This means it can be mounted by many pods that run on the same node. And this can actually be quite confusing. We've seen many users get caught off guard and ask us questions. Oh, you do support read-write many. And we have to explain, no, we don't. This is just the way that the read-write once mode works, where as long as the pods are running on the same node, they can get access. So read-write once pod is a recent mode which enforces read-writes to a single pod rather than to the entire node. So another thing we get asked a lot by users is, why can't I just mount the volume on multiple nodes? And unfortunately, widely used file systems such as XFS and ext4, they're not distributed file systems. So you can't simply just mount those volumes from different nodes. Typical solution that we suggest is to place an NFS server on top of a read-write once volume. And I think many other storage provisioners recommend doing this, and some even do it by themselves so that the user doesn't have to. So let's say you're deploying a highly available application, such as a database, as I mentioned before. And each instance of this database wants to consume its own independent volume. And the advantage of that is, if one of those instances goes down, you still have your database working with the other replicas. So far, so good. But consider what happens if the PVs are created, if the PVs for all those volumes are created from the same storage pool. If that storage pool fails, your highly available database actually will fail because it has no more access to the storage because it was shared. So you should check with your storage provisioner how to use anti-affinity between these volumes, not just for the applications, but for the storage itself. Just as an example, for MyStore, we have a STS affinity group option on the storage class, which will basically create anti-affinity for independent volumes, part of the same stateful set. We've also noticed that a lot of folks end up not setting up alerts for their volumes, for the storage. And this can be especially bad for thin provisioned volumes. So you should regularly monitor your storage usage. Tools like Prometheus and Grafana can help you visualize and get critical alerts. So why is this a bigger problem for thin provisioned volumes? So if you have a thick volume and you're running out of storage, maybe that will impact you and it will prevent creation of new volumes. But existing ones maybe are not affected because they're thick provision. They already have all the data they need. But if you have a thin provision volume, then running out of space can actually impact existing volumes. So suddenly your application can start to fail because there is no storage available for existing volumes. And this can be especially bad if it affects, again, a highly available application such as a database, if on each of the nodes the fin provision storage is running out. So snapshots are now widely used in Kubernetes for local backups, remote backups, but not all snapshots are equal. So you should be aware of different kinds of snapshot consistency. Application consistent means they use an application-specific interface, which will quiesce and freeze the application itself. File system consistent does the same thing, but only at the file system level. And some drivers also use sync, which is just a best effort to flush data, but it doesn't actually freeze the application or the file system. So having a low consistency might actually impact your ability to recover data. So with OpenEBS, we have two different types of drivers. We have node local and we have replicated. Node local are the ones where the application is pinned to the storage node because the storage is not replicated. Then we have replicated where the application can run on any node and the storage will be replicated across n nodes. So previously we touched a bit on the advantages of having the application and the storage on the same node, right? Because you're not paying that network penalty, you're getting better performance. So we've had still several people mention that they prefer using, I'm getting around myself. Storage which is local to a node or app may give you the best latency and throughput. So replicated databases, they manage replication themselves through the stateful set. So in many cases, they prefer not to use replicated storage because why duplicate the efforts they're already doing? Single node edge workloads are actually a good example for this as well. And we have a lot of people using this way. For example, our node local ZFS provisioner, where people can use it on NAS boxes, for example, that sort of thing. Replicated storage will give you high availability, but it will cost you additional storage, higher latency, and throughput. The disparity between the different storage plugins will vary. The disparity will vary dependent on the different storage plugins, depending on how many replicas you're using, whether your system is using caching, what's the interconnect between the nodes, the protocol you're using, etc. However, we still have people that prefer to use replicated for their databases because it just ensures multiple levels of redundancy and it avoids having to rebuild the data at the application level and instead just relegating it to storage. So there's pros and cons to both. So as previously mentioned, wait for first consumer can work very well when the application is basically pinned to the local storage. And this is actually using the topology feature, which can ensure that the pod is always scheduled on the same node. So even if you kill the pod and recreate it again, it will be created on the same node. This has a disadvantage that if your node local provisioner doesn't allow for remote access, then the application is effectively stuck on that node. So we're almost touching on node kind of failure on these scenarios. So let's consider that. When one of the storage node fails, the remote application should be able to resume I/O, provided that the volume is replicated to another non-fail node. And this is one of the benefits of replicated storage, is its robustness in this scenario. But what if it's the Kubernetes worker node where the app is running that actually goes down? Then I guess the pods should just move to other nodes, right? Unfortunately, no. That may not happen. When a pod has no volumes, for example, or it uses read-write many volumes, then yes, that can happen. The pod can move to other nodes. But if you're using read-write once volumes, then that becomes a bottleneck. Because remember, read-write once, the volume should be available only on a single node. If the pod doesn't terminate properly, then a new version of the pod will basically fail to start due to multi-attach errors. This is expected, and Kubernetes doesn't know that it's safe to actually move the pod because the node could still be up and actually not down. Then it might have caches that actually have data, valid data still, so it's not safe to do it. So let's have a look at some of the options to help with this failure shutdown mode. So there are two different options, graceful and non-graceful node shutdown. Non-graceful node shutdown can be used to basically trigger a forced deletion of the pods and the volume attachments that are telling Kubernetes that this volume is attached to this particular node. So if you do that, you can get around the issue and you can then recreate your pods on a different node. But please be careful and ensure that the node is indeed shut down. Otherwise, you can actually, if the node is not truly shut down, you could have data corruption if the node pops back up again. And this has actually happened before to a user. So on OpenEBS MyStore, we have some mitigations, ensuring that the previous nodes cannot connect to the volume. However, there is still an issue if the volume gets mounted back on the same node. And we are working on a fix for adding a safety net feature for that, even though we still don't recommend doing it. Graceful node shutdown, we just, at the moment in beta, as far as I know, graceful evicts pods during node shutdown. But unfortunately, it doesn't quite work well for us. It doesn't wait for the volume teardown to happen, which can again prevent the pods from running on a different node due to the multi-attach errors. So you may have to end up cleaning up the pods and the attachments yourself, and then we recommend using a combination of both the graceful node shutdown and then the non-graceful node shutdown, which will then trigger the deletion of the pods and attachments. So CPU Manager has a static policy which allows containers and guaranteed pods with integer CPU requests access to the CPU on the node, exclusive access to the CPU. For a pod to be guaranteed, every container in the pod must have CPU and memory limits, and the CPU and memory limits must be equal to their respective requests. And fortunately, it's easy to miss this, and that every pod and every container in the pod must abide by these rules, and then the container can be a guaranteed quality of service. So you should always check if your pod is actually on the guaranteed quality of service. So CPU isolation helps prevent certain cores from being used by system threads. So for example, you can set isolation on core 10 and 12. Pairing this, however, with a Kubernetes exclusive CPUs can be quite complicated if you need to reserve a lot of CPUs, but you don't want to isolate them all, because maybe you just want to isolate 2 of them for a particular use case. An alternative solution can be to exclude the ones that need isolating with reserved system CPUs, so Kubernetes will not make use of them for your pods. And then you modify your applications to actually set their own affinity to those specific cores which are isolated. So as an example, MySR uses polling for improved performance. And if there is another system task, let's say another kernel thread which can also sometimes poll for performance, if they're on the same CPU, then that's not ideal and you'll suffer performance decrease. Data migration is the process of basically moving data from a source storage to a destination storage. There are different techniques and methodologies for data migration, and it can migrate within the same cluster or a different cluster. So you can use this using backup and restore tools themselves. For example, Valero is one that we usually recommend. And there are also, however, rsync-like data migration tools like volsync and pvmigrate. And I quite like pvmigrate. This is actually the one that we've recommended our users to migrate from an old OpenEBS engine to a new OpenEBS engine. A trick you can do with data migration is if your provisioner doesn't support volume expansion, and we didn't always support it on Mayastar, then you can use it to move data from a smaller volume to a bigger volume. It's a bit of a hack, but it does the job. And if you like eye candy, then you can see pvmigrate working, which, yeah, I like. Okay, thank you for listening in. Just some information about DataCore. We sponsored the OpenEBS engineering for Kubernetes. We have commercial support for OpenEBS. And there are some links here if you want to check it out. Yeah, thank you very much.
That was a really great presentation. I must admit, when you showed that data leak, I was like shocked. I would have definitely, I think I've done that in the past. Okay, so the first question is not really a question, but someone thanks you for making them aware of read-write once pod because they didn't know about it and I also didn't know about it. So I thought it would be lovely to tell you that. The next question is, I don't know if you saw Kelsey Hightower's fireside chat.
No, and unfortunately, no. I've got a bit of a stomach bug at the moment, so yeah.
All right, don't worry about it. So Kelsey said that persistence, like databases, should be separate from Kubernetes, and that was his like one thing that he thought shouldn't be used with Kubernetes. So do you agree or disagree with that point?
I think I'd have to see the reasons he mentioned for why that is the case. In certain cases, I'd probably say yes, if you're tearing your clusters up and down all the time and maybe you want your applications to be preserved, then maybe you can keep your databases outside of the cluster. So for example, if you're upgrading your clusters a lot, you might not want your applications to restart, but I don't know without knowing exact details.
Yeah, so he said that, you know, as if it's torn down, then you're gonna lose your data. Okay, the next one is, does the wait for a first customer setting hide potential performance problems until a rescheduling of a pod happens?
What kind of potential performance problems? Is it from, oh no, it's online, right? Oh.
So you said that wait for first customer usually, should I wait for the mic?
I think we can hear you, but I'm just gonna give it to you.
Check, check. Okay. Yep. So you said for the wait for first customer setting that the pod is usually scheduled on the same node where the storage then happens. So if you evict the pod or whatever happens and it is really scheduled to another node, you now have the data path moving through the network of the cluster. So the initial thought of this would suggest to me that putting that on the first node in the first place is working fine because it's a local connection, but as soon as you move the pod away, you have network in between, and that might cause potential problems that appear way further in the timeline, and so you're searching for whatever reason, and you might miss that.
Yeah, I guess that's a valid case, and it probably doesn't fit everyone setting it up in this specific way. And for example, if you use replicated storage, then you're always going via the storage anyway with a lot of the CSI drivers. So yeah.
And the very last question is, does it make sense to manage CSI-compatible storage on-premise to use as a persistent storage and orchestration tools?
I think so. I guess it depends. So I'm assuming that this question means you're already using Kubernetes as a storage orchestrator. So in that case, why not also use CSI? Because it's already there and you don't have to develop your own custom solution. So we do have a cloud storage provider that uses OpenEBS MyStore, and they do exactly that. And I think Microsoft Azure is now also making use of their own version of OpenEBS, which does it. So yeah, I think it's a good use case.
Okay, let's have one more round of applause for Tiago. Thank you so much.